predictability of models, there's different challenges, as I said. So we have computational complexities, having the kinds of computers allow us to do the types of problems we need to do. And oftentimes it's not enough to look at one single sort of piece that's very small, say 5 atoms, but actually we need to look at millions of atoms with a complexity in the description of the chemical interactions that's complex computationally. So it takes a lot of computational power to solve the equations for million or billion atoms while describing the chemical interactions at a level of accuracy that's important. Now, that just simply wasn't possible a couple of years ago. Possible now, but by itself it's not enough, because now you need the validation to see when your fidelity of the model is enough to describe the phenomenon. So that's the other end. So sort of two things came together. We had more and more computational power, models became more accurate, but also we had experimentation that sort of give us data, quantitative data that told us now exactly when the model is good enough, if you wish, for that particular case study that we wanted to do. In different scales, we can look at different things. We can take single molecule spectroscopy, which basically is sort of the most direct way of validating models that start at the molecular scale. We would experimentally, people now can take a molecule and attach a bead on one end, another bead on the other end, like a little ball, right? And then you can fix one ball, glue it to the ground if you wish, and then take the other ball and pull it. And that's done with light, with laser. That's called optical tweezers, and these kinds of experiments allow us to pull on these molecules and basically stretch them, just like engineers have been pulling on anything since engineers started building things, because they wanted to know the strength and modulus and stability of materials. That's a setup that can be done computationally as well, right? We can take a single molecule, we can simulate very truthfully the solvent, the water molecules. Sort of things come in that are very complex now. There are solvents, there might be salt, there might be certain types of ions in the system. And then we have the description of the molecule itself, which might be a protein or any kind of molecule that we might want to build our material from. And we can probe how strong it is, how it actually breaks, and what happens if you expose this molecule to extreme conditions. Extreme conditions might be temperature, it might be pressure, it might be extreme pH. You think about corrosion, right? There's many different types of things we can do, and the chemical scale there is essential. So now we have something like this, and now if we imagine at larger scales, we might want to work with something that works at scales of micrometers, right? And so we have models now, experimental models that are based on called MEMS devices, micro electromechanical systems, which allow us to pull on entire fibers now, which might be micrometers long and a few hundred nanometers diameter. It's very, very small samples still, but basically encompassing thousands of molecules, right? So now we have a tool where we can probe the next scale when molecules interact and they form a structure, right? And that again can be done computationally, because we have computational power, we have these models that allow us to do this, and we can pull on them, we can bend them, we can map their structure on the surface, and see how the structure changes as we change the water environment or the solvent or pressure, temperature, etc. And then that can be done again at different scales, larger scales, when eventually, in the case of a spider web, if you probe a spider web, you can do this yourself. You can actually go out and take a little a steel needle or something like this and pull and poke on the spider web, deform it, and that is sort of the easiest scale, if you wish, the most traditional scale that engineers have done for many years. But we can do all these different scales computationally now and link them with relevant experimental studies.